Still unmuted? All right, well, I think we've been 5 minutes, so I'm going to take this opportunity to introduce you all to Dr. Jessica McGyver, who is a senior postdoctoral scholar in experimental physics at the LIGO laboratory at Caltech in Pasadena, California. She grew up in the capital region of New York and graduated from, is it Mohonasen High School?
Mohonasen.
Okay, thank you. And she got a bachelor's degree in physics and journalism from Syracuse University in 2009, where she first began work on exciting gravitational wave research for the LIGO detectors, working with Josh Smith and Peter Salson. She graduated with a master's and a Ph.D. in physics in 2015 from the University of Massachusetts Amherst under the mentorship of Laura Padanati. She has 11 years of experience in gravitational wave data analysis and wrote her Ph.D. thesis on extracting the gravitational wave signals of core collapse supernova from noisy advanced era interferometer data. She's currently based at Caltech, and she's one of the leaders in the LIGO detector characterization group in the award-winning International LIGO Scientific Collaboration. She was based at LIGO Livingston site, that's in Louisiana, correct?
Yes.
At the time of the first detection of gravitational waves and the merger of two black holes, which earned the Nobel Prize in Physics to Rai Weiss, Kip Thorne, and Barry Barish in 2017, she directly contributed to the growing number of exciting gravitational wave discoveries, along with her colleagues at LIGO-Virgo. She's a laureate in the Special Breakthrough Prize in Fundamental Physics in 2016, and a co-awardee of the 2016 Gruber Foundation Cosmology Prize, the UK Royal Astronomical Society Group Achievement Award in 2017, the Bruno Rossi Prize 2017, and the Princess of Asturias Award for Technical and Scientific Research in 2017. And I believe a year ago, you started at UBC.
That's right, yes.
All right, so take it away, Jess.
Thank you so much, Charles, for that very lovely introduction. That's quite a mouthful. I appreciate you reading through all of it. I do indeed have some exciting news to share with those who have joined. So I did indeed start at the University of British Columbia in July as an assistant professor. So I'm now based here in the Pacific Northwest indefinitely. So I'm very excited about that. And I have a question for you. Maybe I'll direct this at Charles. What is your dream length of time for a presentation about gravitational waves?
Usually the speaker gets the job done within an hour, so.
Okay, that sounds good. I'll try to leave as much time as I can for questions because that's my favorite part.
Sounds good.
All right. So thanks a lot, everybody, for joining. It's a real pleasure to be with you here. I hope everybody is doing well. So let's see. Can everybody see my screen right now?
Yes.
Excellent.
Yep, we got it.
Great. So I'm going to be telling you about some exciting research. So I work with, as Charles mentioned, the Advanced LIGO detectors. So we sense gravitational waves through space-time. So we're going to learn how this all works end to end. It was really neat for me to hear the updates about what's happening in the sky because I do none of my astronomy with light. I do all of my astronomy with space-time, so I have very little sense of whether or not it's day or night. And something else that I would just like to mention, so we're going through a tumultuous time right now with the pandemic and also with violence, particularly in the US. So I wanted to recognize that a lot of these really exciting and wonderful scientific results that I'm going to share with you are made possible in part by the contributions from many Black colleagues of mine, and some of them are really deeply impacted by this issue. All right, so here we go. So please feel free to ask questions anytime. I'm happy to hear them through the ether by voice, or I'll try to keep an eye on the chat as well. Oops. So I like to start with what are gravitational waves exactly? So this is maybe easier to get an intuition if we think about waves in the ways that we're used to seeing them. So this is a movie that I quite like, so this may look familiar to all of you on the Sunshine Coast. So essentially what we mean when we generally think about a wave is you have some transfer of energy, some transfer of momentum through some medium. And the example that we think of generally first when we think about a wave is water. So this is a good example here. So this is also true of many other media. So there are examples of wave behavior pretty much everywhere in nature. So what I'm about to show you, this is a time lapse, and these are not water waves, but these are actually cloud waves. So I'm going to play this. So what you're seeing, these oscillations, it's actually a time lapse of clouds. So this is taken from the top of a mountain, and here you can see them beating up against the shore of this mountain, much like you would water. So we see this wave-like behavior in many, many different areas in nature. And then, of course, one of those is light. So as I'm sure all of you are very familiar with, so up until the first direct detection of gravitational waves in 2015, everything that we learned about the universe was through light, we learned about the solar system, we learned about our Milky Way, we learned about the expansion of the universe and dark matter and black holes with light. And we can tell quite a lot by eye alone. We can see the components of our solar system, we can see our own Milky Way, and we have gained a lot more insights, as was mentioned earlier in the call, as our instrumentation has advanced. So this is another time lapse that I really love to show, which shows the leaps in our view of the world and our view of our own worlds through the improvements in our instruments. So this is a time lapse that was taken from the International Space Station. So this is a view of the world and one of the great mysteries for a long time, which is the Aurora Borealis. So as our instrumentation continues to improve, we're able to turn this perspective outside of our own Earth and out into our own galaxy. So what you're seeing here, so this is the Crab Nebula. So it's about 2 kiloparsecs away. So this image was taken with the Hubble Space Telescope. And what you're seeing is the remnants of this gigantic explosion. So this matter that was cast off into space. And at the center of this matter is a very, very tiny, completely invisible on this kind of a scale, dead core of a star. So this is the remnant neutron star, the collapsed core of the massive star that's left over after the outer parts of the star have bounced off of it and been scattered out into the galaxy. So let's remember back to neutron stars as dead cores of stars, because this will come up again later on. So our instrumentation, as it's continued to improve, we've been able to see with light deeper and deeper into space. So this is an image that I quite like of a galaxy that's millions rather, of light years away. So this is taken with Keck, which is also mentioned earlier on. And what we've gotten the picture of, so we have, as our instrumentation has advanced, our evolution of understanding of what kinds of lights can tell us has also evolved. So all the way from gamma rays to radio waves, we now are building this complete broadband image of the sky over time. And this has revealed many things, including some of the first insights about black holes. So with light, we can use light to estimate the mass of a black hole if it has a companion. So what you're seeing here, so this is a black hole and its companion star, and the black hole is accreting material, and this is causing an X-ray emission. So we have some light source, essentially, some source that's illuminating the location of the black hole, and we have the light of the companion star, and we can use their orbital period to infer what the mass of the black hole is. So these are some of our first estimates of black holes, particularly in our own galaxy. So now we are also able to image black holes with light. So this is the now famous image from the Event Horizon telescope. So the way that this kind of imaging works, so in order to resolve an image, as you all well know as astronomers yourselves, so this depends on the diameter of the telescope. So in this case, it was the diameter of the whole Earth, so many, many different arrays of telescopes that were all used to generate this image. So this works really well if you're trying to resolve an image of a particular size, particular different distance away from essentially your telescope size, if you like. So this is a brilliant advance, but it's also only going to be applicable for a very limited range away from the Earth. So there's only maybe a handful of candidates that will be able to use this technique with. And this brings us to gravitational waves. So this is a completely new way of learning about the universe, which is completely independent from light. So gravitational waves are tiny perturbations in the fabric of space-time itself. So they propagate essentially completely unaltered through vast distances of space. So this makes them incredibly difficult to detect, as you'll see, but it also gives us this really crystal clear picture of the dynamics of the systems that are generating them. So with gravitational waves, we never need to worry about if it's daylight, we never need to worry about dust or other obstacles that the gravitational waves will encounter between their source and us, the observers. We get that image, if you like. Some liken it to sound waves. But this will travel to us and we'll be able to get this essentially completely pristine sense of the system that generated it. So I am going to teach you everything you need to know about general relativity. So I hope you came prepared to learn some general relativity theory today. So everything that you need to know to understand gravitational waves is captured in this image. So essentially, you're looking at Einstein's central equations here. So you have one side of this equation that's relating the distribution of matter and energy, and then the other side of the equation is telling you about the curvature of space-time. So John Wheeler had a really nice quote that relates these two together. So you have matter that's informing space-time of the curvature, and then the curvature that's actually informing the dynamics of the matter that's in it. So this is represented really nicely with this image. So the green grid is space-time and the curvature that's induced by these massive objects. So we have a sun here, and then very much not to scale, an Earth-like planet near it. So gravity, in the way that we experience it, what we are experiencing as a pull, as a force, is actually these objects that are trying to travel in a straight line around this curved, warped space-time. So this is essentially what gravity is. And like any other sheet, so you can make some really, really interesting predictions. So some of the predictions for gravitational waves are black holes. So of course, we have observed these now in multiple different ways. And you can see around this artist's impression, the simulation of a black hole, this bending of light, this warping of light. And this is another prediction of general relativity. So what you're seeing on the left here, so we have, let me see if I can find a way to show my cursor. It doesn't look like I can, so I'm gonna use my words to the best of my ability here. So if we're standing on the Earth, what we're going to see, instead of the true position of this distant star, we're actually going to see the star, which now is, the light is traveling very close to the sun, but it's being bent. So the sun, this star-like object that's closest to the Earth, is warping, it's curving the space-time. So the light from this distant star is going to be curved until it actually looks like the star is in a different position than it actually is. And this is very testable. So this was actually measured in 1919, so over 100 years ago. This is one of the first major confirmations of general relativity. So this is the headline in the New York Times, "Lights all askew in the heavens." And this is essentially the experiment that Eddington and his team did. They waited for a solar eclipse. Oh, sorry, is there a question? Aha, I thought I'd heard somebody. Well, don't hesitate to ask if you have one. So the experiment done by Eddington and his team in 1919, so they targeted 2 locations in the Earth, just in case there was cloud cover. So one was in Africa and one was in South America. And they funded this expedition to do exactly this measurement, to gauge the change in location in the sky of a known star during a solar eclipse. So coming back to our analogy of space-time as a sheet. So essentially what space-time is it's this weaving together of 3-dimensional space. So you can go up and down, you can go front to back, you can go side to side, and you can do some combination of all of these. And that's how we experience 3-dimensional space. And then you weave this together with time. And time only has one direction. Time can only go forward. And mathematically speaking, we can think about this like a fabric. And like any other fabric, like any sheet, if we perturb it in some way, just like throwing a rock into a pond, we're going to get waves. And that's what gravitational waves are. So they're generated by some kind of accelerating matter. So even now, as I'm moving my hands, I am generating gravitational waves. So something that I really like to point out with gravitational waves, I have covered my equation here. So I'm going to do my best to recite it from memory. So the gravitational wave amplitude, unlike light, this is one of the really big, powerful elements of gravitational wave astronomy, is that the amplitude of gravitational waves, so we write this as little h, or gravitational wave strain, it falls as 1 over the distance between the observer and the source. So it's written as 1 over r here. So this is unlike light, where if you're counting photons, if you're looking for flux, then your power is going to fall, your amplitude rather is going to fall as 1 over the distance squared. So we can probe these really incredibly vast distances with gravitational waves. So something else you'll notice is that this space-time strain amplitude, this what we'll see is the stretching and squeezing of space-time, is proportional to a really, really small number. So that's capital G, the gravitational constant, divided by a really, really big number. So that's c, which is the speed of light. So this effect is absolutely minuscule. And then lastly, so what is actually making the gravitational wave? So the derivative that you're seeing here, so that means the acceleration of some asymmetry in the system. So we'll see that one of the most well predicted sources of gravitational waves are 2 compact objects like black holes or like neutron stars that are going to be inspiraling very, very fast, very close to the speed of light. And this is going to generate a gravitational wave signal that's going to be very high amplitude. So the heavier the system, the more massive the black holes, the louder, if you like, the system will be, and the farther away that we'll be able to see it.
Can I just interrupt here?
Sure.
Yeah, okay. By the way, Charles, I don't see a little button to say, you know, that I've got a question. So you just butt in by unmuting. Is that the idea?
Yeah, I've got everybody basically muted until they unmute themselves, but you can send a chat message. I'm watching the chat.
Oh,
okay. If you have a question, you want to send it that way, I'd be happy to pass it on, no problem.
Okay. Okay, so back to the question then. You said that light falls off as 1 over r squared, 1 over distance squared. And then I thought you said gravity falls off as 1 over the distance to the 4th. That's worse, right?
So let's see if I can manage to grab my chat window here. I brought it up in the hopes that I would be able to help manage questions, but now
Can you, yeah. If you're blocking your formula, you can move something.
Yeah.
Okay.
I am. Let me see if I can. There I go. Brilliant. So yeah, so what we're seeing here, so this is actually the speed of light. So the two constants that help me to reinforce how small this effect is the gravitational constant, which is 10 to the power of many, many negatives. And then this is the speed of light, which is 3 times 10 to the 9th. And then you take that to the 4th power. So the amplitude of gravitational waves actually only goes as 1 over r. So we more physicist types tend to use r for distance.
Yes. Yeah. No. I'm a physicist type.
Oh, great.
Okay. So then I misunderstood. I thought you were saying that it dropped off as 1 over r to the 4th. It's 1 over r.
Indeed. Yes. Happily, that is true. 1 over r.
So how does that conserve energy or whatever? Or is that not an issue or what?
Well, so the way that I like to think about it is that if I am an electromagnetic wave, so if I had a way to measure the amplitude of an electromagnetic wave directly, then I would be able to do something really similar. So I would be able to make a measurement with an amplitude that falls off as 1 over the distance away between me and the source. But what we normally do is we measure power. We measure the flux. And so the area is what's going to give you the dependence of second power.
Okay. So is this similar to or different than light? In this falling off?
I think of it as it's analogous to dipole radiation in electromagnetism, but here, so you can think of, sorry for the physics speak, everybody. So you can think, we'll see that our detectors function kind of like a direct, transducers. So we're directly transducing the space-time strain that's stretching into our measurement of amplitude, whereas for light, we don't have a good method to do that.
Okay. Thank you.
Yeah, fantastic questions.
Okay.
How's everybody else doing? I've closed my chat now, so I'm relying on you, Charles.
I want it.
Okay. Well, if there are any other questions, please let me know.
Well, this is John Thompson from Ottawa. I have a question there about the image we just had. That suggests that the propagation is two-dimensional, like ripples on a stream or a surface of water. Does that mean that Earth happens to be directly in line with the plane of the orbits?
That is a fantastic question. So you're right, this is a two-dimensional projection that you're seeing here, just for ease of understanding. So we'll see that gravitational wave emission is actually three-dimensional, but there is a component of the amplitude that's related to if you're seeing it. So if this is the angular momentum of the system, if you're seeing that sort of from above, you're going to get the maximum amplitude. And if you're seeing it from the side, you will still see gravitational wave emission, but it will be reduced.
Yeah, okay. Because I remember having a discussion like this with some colleagues in Ottawa, and my guess was that the reason that the strength is inversely proportional to 1 over r and not 1 over r squared was because it was two-dimensional propagation and not three-dimensional. I don't know if that was correct or not, though.
It is indeed three-dimensional propagation.
Okay, yeah.
I was interested, it's Brian. I was interested in the last month. It sort of came up into my radar. It's likely the knowledge has likely existed for a while, but the headline was that the universe is flat, and maybe it's a question tangential to what we're talking about. If the universe is flat, that to me means it's only in 2 dimensions. But if the universe is flat, how can there be any amplitude of anything? Is one simpleton's question. And also, how do we have the sense of being able to move in 3 dimensions if the universe that contains us is only 2 dimensions? So can you give an answer to that somebody like me could understand?
Well, I'm going to do my best. So yeah, that's a good question. So let's maybe start from the premise that we are indeed in 3-dimensional space. So we can all move in 3-dimensional space, and gravitational waves propagate in 3-dimensional space. And now let's suppose that we need to find a good way to describe what the universe is doing on a really, really, really big scale mathematically. So one of the ways that we might choose to describe it, let me see if I can find some good words for this. So if we describe it, if we try to reduce the number of terms or qualities of the universe that we need to describe what the universe is doing, then we could think about, well, is it, overall in the grand scheme, is it expanding? Is it contracting? Is it staying as it is? And then how are the different elements of the universe, or wherever you may be in the universe, related to each other, and how they're executing that motion? So this is where sort of the math jargon of flat comes in. So this is some really, really big scale description of the universe and how very disparate parts of the universe are related to each other.
Thank you.
I hope that was helpful.
I'll think about that.
Yeah, I will too.
Ryan, I'll share a link with a Spacetime show by Professor Matt Dowd, and he describes the flat stuff.
All right, thank you.
Question from Richard here. Can you hear me?
Yes, we can.
Okay. I remember worrying about this about 30 years ago when all my brain cells functioned. If you look at the rubber sheet analogy, you had a slide earlier on where you have a sun and a planet. Yes, you're taking 3 space and you're projecting a property of it which is isotropic in all 3 axes and representing it as amplitude on a 2-space plane, right?
Yes, indeed.
So theoretically, if you moved to the right 90 degrees and you look back in the same fashion and you project it onto a vertical, you'd see the same thing. So you have a 3-dimensional compression of space-time around a mass, right?
Yes, you would.
And you're sectioning it. And if you looked at the intensity of that, or density of the space-time, that's the change from a flat plane that you're portraying on that screen, right?
I would say so.
Thank God I haven't lost it all yet. Good, thanks.
Wow, that was the easiest question yet, a question I don't have to answer.
Well, you did, you said yes.
I did, yes, that's true.
Thank you very much.
Oh yeah, wonderful questions. If I had known that there were so many physicists here, I think I would have maybe had more equations for you all to chew on. How's everyone else doing?
It's Brian again.
Hi, Brian.
I have another question. It's a question that I've asked before. and I'll likely continue to ask anyone that comes along that has yours or similar CVs. I figured, it occurred to me that yes, the Bell technicians discovered the cosmic background radiation. And so I was wondering whether there was now that we have LIGO or LIGO, could we start to answer the question or measure and take it beyond theoretical, that there would be a gravitational equivalent of a residual, instead of a residual electromagnetic hiss, there would be a residual a gravitational buzz or a tremor. And so that was one question I've had. And so then the next question is, has LIGO tried to, and hasn't been successful at finding the cosmic background buzz?
That's a great question. So let's maybe forget where I put this. Here it is. Right, so you would indeed expect to see some gravitational wave amplitude for any kind of asymmetric acceleration. So we could conceivably have generated such a buzz, especially early on in the universe. So yes, this is something that the LIGO-Virgo collaboration is looking for, and no, we have not found it yet. So it depends on your model for how you would, what you would predict this asymmetry to look like in the early universe, whether or not LIGO and Virgo would be able to see it, or whether you need something like LISA, the space-based version.
Now,
Yeah.
I'm gonna, one last little thing.
Sure.
I'm going to talk about something that I've never understood, and that's the uncertainty principle. And I found that a very hard thing to get my head around, always. And I was just wondering if there's any connecting observational physics with the theoretical. Is there any possibility that this buzz, where the whole of space-time is wiggling, how can we possibly ever get a definitive measurement on anything? There's always going to be well, to use the term, there's always going to be an uncertainty. And so I'm just desperately groping to wonder if the gravitational buzz is in any way the physical, tangible basis of, I'm assuming the uncertainty principle is generally a mathematical idea.
Well, that's a fantastic question. And so we do think a lot about, we tend to call this in a jargony way, shot noise. So we call it quantum uncertainty noise. But we need to deal with this physical manifestation of the uncertainty principle actually with our detectors. So you've delivered us a fantastic transition that I'm going to take advantage of. So let's talk about how gravitational waves propagate, then we'll talk about detectors, and that'll bring us right to the uncertainty principle. All right, so what you were looking at, so this is for a gravitational wave that's propagating down through this tube, and what you're seeing is this stretching and squeezing effect. So this stretching and squeezing, this is directly proportional to this strain amplitude that we just defined. So this happens to be for a circularly polarized wave, and what that means is that it's going to stretch and squeeze in one direction, and then it's going to kind of shift 45 degrees and do the same thing. So for the physicists in the room, that's two orthogonal polarizations. But this is the physical manifestation of this change, this relative stretching and squeezing, this relative change in distance between two different directions that we can actually measure. So if I slice that tube and I just take one slice of the tube and now the gravitational wave is propagating in or out of the screen, the gravitational wave strain measurement that I'm making, or the strain in this case, this change in length over length, is the time series that you're seeing at the bottom. So this is essentially what we want to measure. We want to measure the gravitational wave strain as a wave is propagating in or out of some plane. And we're going to see that this is a great way to design our detectors. So it's this stretching and squeezing of space-time that we actually measured in 2015. So thinking right back to the time series that we just saw, what you're seeing, that's real data from gravitational wave detectors. This is the amplitude of the stretching and squeezing of space-time. So we've also decomposed this into frequency over time. So this is helpful to be able to see what the dynamics of the system are. So the system that generated the signal, so this is two black holes, roughly 30 times the mass of our own sun, that inspiraled and merged together to form a much larger black hole. So what we would expect to see is they're spinning faster and faster, so the frequency of our gravitational wave is going to go up. And this is the prediction of general relativity, and this is what we see here so beautifully in our data. So if we were able to see two black holes with a telescope, so this is a simulation done by the SXS collaboration of what that might look like. So here we see this warping of light around the system, and we see these two black holes orbiting each other closer and closer together until they merge. And then this final black hole rings down. And we can also take a look at what this looks like in space-time. So what you're seeing here are two black holes, again, roughly 30 times the mass of our sun. And the colors here, so this is representing the warping of space-time. So what we see, we have these two black holes, they're orbiting each other. Now, general relativity says that they should be radiating away energy in the form of gravitational waves. And as they radiate away that energy, what's going to happen is that their orbits are going to spin up. They're going to start spinning faster and faster until they're approaching the speed of light. And now, as they get closer and closer together, we're reaching the peak amplitude of the gravitational wave emission. And for a system like this, so two black holes are roughly 30 times the mass of our sun, right now is the moment where they're releasing about 3 solar masses worth of energy in an instant. So the moment that two black holes of this size merge, they're, in terms of power, the most luminescent object in the whole universe. They'll outshine every star in every galaxy in terms of the energy they release. And then these gravitational waves will propagate away at the speed of light. So one way that we can use the excellent signal processing that's in our brains to interpret our data is through sound. So I'm going to play for you the same data. So this is the data as it was registered in the 2 LIGO detectors, and we'll hear more about where those are. It's pretty neat, right? And then we also like to alter this, speed it up just a little bit so that it's easier to hear that whoop. So those are the famous sounds, if you like, where it's taking our space-time strain data and turning it into an MP3 file. So one of the wild and wonderful coincidences is that the frequency range that we're sensitive to in LIGO happens to coincide roughly with human ears. So we can take our data and then we can play it through a speaker and our brain can pick up on all of these patterns. All right, so this brings us all the way to how do we do this? Coming back to the uncertainty principle, which we do think quite a lot about. So this is the basic idea. So remember again, we have some stretching and squeezing of space-time. We're trying to measure this relative change in distance. So the way that we choose to do this is with laser lights. So here now we have 2 mirrors that are measuring this relative change in distance. So let's follow the path of the light. So we split the light with a beam splitter and half of it travels one way, bounces off of this mirror, and then half of it travels the other. This is, we'll call it the blue direction. They recombine at that beam splitter, and if there's no relative change in distance between those 2 mirrors, no relative change in length between the arms, we see nothing. But if we start to introduce this relative change in length, the stretching and squeezing of space-time, we get this direct measurement of the amplitude of the gravitational wave as a phase difference between these 2 paths of light. So this is roughly how it works. We have 2 of these detectors. So one is in LIGO Hanford in the desert, and that's actually only about a 5-hour drive from here. It's directly south of Chime. If you ever want to make the trip, it's a beautiful drive. And then the other is in the swamp in Louisiana, as Charles mentioned. So here's an aerial image. So this is, these are 4-kilometer long interferometers where the light that's circulating is traveling 4 entire kilometers, and it's making multiple round trips. This is one of the largest vacuum systems that's enclosed in the world, second only to CERN. And then the optics that you were seeing aligned, so these are really important for us to leverage in order to reduce this quantum uncertainty noise that we have. So coming back to the original question about the uncertainty principle, so something that we need to think about in terms of physical manifestations is that what we're doing when we're measuring this phase difference is we're essentially counting photons. So we have some photodiode and we're just counting photons as they arrive, and then we're mapping this to space-time strain. So like any other counting experiment, so you brought up the mathematical nature of the uncertainty principle, like any other statistics, any other counting that you would do, you have some fuzz there. You have some measurement fuzz, and that has to do with the quantum nature of light. So what we can do to reduce this, just like you would do for a counting experiment, is you just increase the number of photons. You increase the number of what you're counting, and then your error is going to go as 1 over the square root of that. And it's the same exact thing for our interferometers. So we are very aware of this physical manifestation of the uncertainty principle, and what we do is we try to circulate as many photons in those interferometer arms as we can, and this pushes down our, we call it shot noise, by 1 over the square root of essentially the number of photons that are in our interferometer arms. So to your point about whether or not the uncertainty principle is contributing to the CMB, there are some interesting quantum gravity theories that speak to what we can know or what we can't know or what we can and can't measure in terms of the CMB and gravitational waves from it. I'm not a theorist, so I'm not an expert on them, but I thought this was an interesting application for the real physics of the uncertainty principle that we have to grapple with.
I'm thinking that when you're talking about counting photons and so on, you're talking about the quantum uncertainty in the electromagnetic field. I'm wondering if there will be, or there is now, but it'll be a matter of discovering it and measuring it as in will be, a realization that there is not an electromagnetic quantum uncertainty, but there will be on top of that, to make matters worse, there will be a gravitational buzz, like a quantum uncertainty with the gravitational field. So that, anyway, I'm not going to answer that for you.
Well, it's a good question. So instead of light packets called photons, the quantum unit that we think about for gravitational waves is gravitons. So our gravitons have such a long wavelength that it's really tough to design an experiment that would detect that effect. So there's an experiment called the holometer at Fermilab that comes pretty close to trying to address a similar question or a related question. But I haven't heard any theories that directly predict that the CMB would have a quantum kind of graviton fuzz to them. But as you say, as our instruments improve and we learn more and more about the universe, we may be surprised by what we find.
Thanks.
Yeah, good questions. So coming back to the quantum nature of this measurement that we're making and how incredibly small these changes in space-time are that we're measuring, this is one of my favorite animations for showing just how small, just how quantum we're able to see. So we're zooming out from a hydrogen atom all the way down to the surface of a proton here. And this is to scale the relative distance that we're able to measure with the LIGO interferometers. So at the time this animation was made for the first discovery of gravitational waves in 2015. This was about 10,000 times smaller than the diameter of a proton. And now we're doing roughly about 2.5 times better than that now in 2020. Yeah, I agree. So seeing this all end to end, so we have two compact objects, they inspiral, they merge, and then the gravitational waves will propagate out at the speed of light. So in the case of the first detection, these were traveling for about 1.4 billion years before they finally reached the Earth. And then we would see, so we registered the stretching and squeezing effects. I like to emphasize that this is vastly exaggerated. You'll see why I like to emphasize that in a couple seconds. I call this the Jello Earth effect. Yes, not to skip. So our interferometers are registering this relative stretching and squeezing. And now here is the actual gravitational wave signal as we saw it in the LIGO detectors on that day. So this is September 14th in 2015. So end to end, you can get a picture of how all of this works. So one thing that was particularly exciting in gravitational waves was this multi-messenger union of light-based astronomy and gravitational wave-based astronomy, where we really gained a huge amount of insight with just one event. So this is a simulation. So here, instead of black holes, we have two neutron stars, but they're orbiting in a similar way. They'll speed up, they'll orbit faster and faster until they start to tear each other apart, and then they're going to merge. And here you're seeing this spectacular multi-messenger array of signatures that we can see. So in order, we saw gravitational waves, and then very shortly after, we saw a gamma ray signal that was registered from this relativistic jet that was emitted shortly after the neutron stars merged together. And then on the span of hours and then days, we saw this kilonova evolve. And we learned a lot of incredible new physics from this one event. We now have some certainty that a very significant fraction of the heavy elements in the universe are produced in this way, so from the collision of neutron stars. We now know that we have some confirmation, some insight into this long-held association between these short gamma ray bursts and binary neutron star mergers. We could test general relativity. We could do a wide range of physics and astrophysics experiments just from this one event. So this is a 2017 discovery. And here's the real data from the discovery of the kilonova. So this is the optical counterpart discovered by SWOPE. So this is the host galaxy NGC 4993. And what you're seeing, so this is a blue kilonova from the day, roughly 9 hours or so after the gravitational wave signal was registered. And then you'll notice that over the course of 4 days, it evolves. It's dimming, it's reddening, and these are the signatures of the radioactive decay of a lot of these heavy elements that we can infer, and we can use to infer generally that this is a really significant mechanism for producing heavy elements in the universe, including on Earth. So something that's pretty neat to show, just to connect further gravitational waves and light-based astronomy. So gravitational wave detectors function rather like microphones. So unlike a telescope where you're pointing it in some particular direction, a gravitational wave is more like a transducer. You put it in the middle of the room and you hear just about everything, which is a pro. So this is a really big boon. So we can hear, if you like, from most directions in space. However, this also makes it really difficult to pinpoint where exactly signals are coming from and do that sky localization. So we rely on our astronomer partners to use these alerts, these predictions of where in the sky, where we must have more than one detector in order to make these accurate predictions, triangulate where in the sky the signal's coming from. But we rely on astronomers to use that information to identify the host galaxy. So the best that we'll be able to do is on the order of about 10 square degrees in terms of localization. But here you can see so the different methods to localize roughly where in the sky this event happened. So this is the same binary neutron star merger that was discovered in 2017. So this ring-like pattern you see here, so this was calculated using the relative time of arrival between the Fermi and integral gamma ray satellites. And then just using the localization of Fermi alone, you get a different two-dimensional array. And then here in green, so this sort of double banana-like shape, so this is what you get from just the 2 LIGO detectors. And very fortunately for us, just about a month beforehand, we had a 3rd detector come online. So this is the Virgo detector in Italy. And this is what happens when you have 3 interferometers. And again, we get this direct measurement of the distance from the gravitational wave amplitude. So we have this 3-dimensional sky map, which astronomers can use to localize galaxies within that sky map. And then this is the actual localization that was used to discover the host galaxy. So this is NGC 4993. So you might be wondering to yourself, okay, well, that's fantastic. We've learned a lot, but what are we learning going forward? What are gravitational waves most useful for? So thinking all the way back to the Crab Nebula, where we saw this remnant of a core-collapsed supernova, and we knew that lurking somewhere in there, that's very, very difficult to see with the telescope, if possible without a magnetic field, somewhere in there is the dead core of the star. So what we're getting with gravitational waves is the dark universe. We're seeing just through the dynamics of these systems what's happening. So what are dead remnant stars up to after they are gone? So this is a simulation from Carl Rodriguez, who's now at Carnegie Mellon. So what you see here is a field of stars. So these are the points of light that are zipping around. You can also see in the warping of space-time, if you maybe squint at it closely enough, you can see black holes that are milling around. And then there are also in this field neutron stars, which are very, very difficult to detect by eye looking at this image, except through their gravitational interactions. So gravitational waves are going to be this brand new probe that are going to illuminate, if you like, what's happening with these dark objects. So what have we learned so far? So this is a slightly outdated even cartoon. So on the y-axis here, you're going to see some numbers. So that's solar masses, or mass of the object in units of the mass of our own sun. And then the x-axis has no meaning at all. This is kind of a visualization to give you a picture of what gravitational waves are bringing to the field of astronomy here in terms of what we learned. So every yellow dot that you see, so this is the mass of a neutron star that was estimated using light. And the two orange dots that you see, so these are the two neutron stars from the 2017 binary neutron star merger. They merged to form another compact object that I think the consensus of the community is that this is likely a black hole, but because we can't tell from gravitational waves alone whether or not it morphed into a black hole, it's got a little question mark there. So what you see above this, so each one of those purple dots are, that's the mass of a black hole that was inferred using light, using X-ray astronomy and some stellar partner. And each one of the triple systems in blue, so this was two black holes that merged to form a larger black hole, and those are what we've detected with gravitational waves. So you can see that already gravitational waves is unveiling this completely new population of very heavy black holes that were invisible to us altogether using light-based astronomy. And they're also highly complementary. So something that's hard to tell from this plot is that what we're seeing with light is what's happening close to us, what's happening in our galaxy and fairly nearby. What we're seeing in blue here from gravitational waves are millions of light years away in very, very far distant galaxies. So we're getting this complementary information in terms of distance. All right, so what have we learned so far from this current observing run? So to put this in context, so I have all three of our observing runs. So this is LIGO-Virgo data taking runs. So we have on the y-axis, this is the number of events of gravitational wave signals. So for O1 and O2, these are just the signals that are gold-plated, very confident detections. For O3, so we broke this up into two chunks, O3A and O3B. For O3, these are all of the events where we issued a public alert. So these are not necessarily going to make it into our catalog of significant events, but it's a rough estimate of how many events we've seen during O3. And then for context, so the first ever detection, so this is all the way on the left here, this happens actually technically before the start of the first observing run. And then the binary neutron star detection that we were just looking at, so this happened, this was less than a month before we ended O2, and here you start to see the rate of events climbing as the sensitivity of the detectors is improving. So what we've announced so far from the third observing run, particularly O3A, is two new discoveries. So what you're seeing on the left, so this is the first event that was announced. This is the second ever binary neutron star merger detected, 190425, which had two neutron stars that individually were very consistent with what we've seen in terms of the neutron star population in our own Milky Way galaxy. But together in the binary, this is the heaviest neutron star binary that's ever been measured. So here, this could be a signal that there's some kind of other mechanism of neutron star binary formation that's extragalactic. And the second event that was announced, so this is binary black hole merger 1904-12. So this is the highest mass ratio where we had a black hole that was roughly 4 times heavier than its partner. And what this allows us to do when you have a mass ratio that's more extreme is you get these, mathematically speaking, these higher order effects, these harmonics, kind of like a tuning fork. If you add the next highest tuning fork, you would sort of get a chord. I think in our press materials, we said it was the same chord as an Elvis Presley song. And what this does is it actually allows us to distinguish. So we actually had a really great question before from what does it look like if you're looking at if the Earth is relative to a binary black hole system, what does it look like if you're looking face on versus edge on to that orbital plane? So that actually having those harmonics, those higher order modes, lets us better differentiate between the amplitude difference that you'd see just from the distance versus the difference from the incline of the orbit. So this was a great discovery. It's the first time we've ever been able to measure these harmonics. And then unfortunately, what you're seeing here in gray, so this is the early end of the run due to COVID-19. So what we're hoping to see in the future, so the fairly near future, so again, our plans are a bit uncertain in terms of what we're going to be able to do and how quickly. So originally we were meant to have our next observing run towards the end of the 2021 calendar year. It's looking likely that that's going to get pushed back to 2022, but that's when we're going to see the LIGO and Virgo detectors at their design sensitivity. And this is before we make future improvements that are going to compress this quantum uncertainty noise, this quantum shot noise. We also have plans to build a third detector. So this is broken ground in India now. So this is a third 4-kilometer detector. And then there's also the cryogenic underground 3-kilometer detector in Japan called Kagra. And something else I like to emphasize is that these stunning results and incredible physics measurements are brought to you by a very big team of diverse people from all over the world. So there's pretty close to 1,500 of us now from 100 different institutions, I think closer to 20 countries now. I'll have to update the slide. But it's one of the best examples, I think, of scientists from all around the world and all different backgrounds working together to achieve something really big. Something else that I love to mention is that if you feel like you would like to help us, or you have some free time, or you're at the airport and you're feeling bored, you should please check out gravityspy.org. So this is our Zooniverse project. And the premise is that you can help us classify our noise sources. So we didn't talk too much about our noise sources in this particular talk, but these are blips and funny features in the data that can mimic gravitational waves. And the more that we understand and reduce these, the farther out into space we're able to see. So if you would like to help us out, or you know someone who's an astronomer enthusiast and likes to play games, please point them to Gravity Spy. Something else I'd like to mention, especially for all of the teachers who are here with us today. So we do have an open science center. There's tutorials there. You can get access to real LIGO and Virgo data. You can work with your students to download the data and process it and get that famous t-shirt image of the gravitational wave strain data and learn some Python programming in the process. So it's fairly accessible and well tested now. So there are some great resources there, including some web courses that you can check out. All right, so I think this is a pretty natural point to stop. We're about an hour, and I suppose I want to save some neat things to say for the General Assembly too. So I will, I'll go back to this slide and give people a chance to jot that down, and I'm very happy to take any other questions you might have.
Thank you, Jess. I had the privilege of going down with a film crew a couple of years ago to LIGO Hanford, and they were down for maintenance, so we actually got inside. It was amazing. But there you can get, there's all kinds of displays in the front there that people can check out if they're down there near Richland, Washington. So I'd encourage members here that want to take that 5-hour drive across the border sometime once the pandemic's been taken care of to check it out.
Yeah, so the state of Washington, last I checked, is also planning to invest in building an educational center, like a mini science museum, if you like. So there is one at LIGO Livingston in Louisiana, and now LIGO Hanford is supposed to get one as well.
One of the things I was told when I was down there, the 4-kilometer tunnels have this dome structure over them. It's concrete. It's bulletproof because people have shot at it.
Yeah, that's not untrue.
Yeah, it's crazy.
Well, where we were really glad to have it for Hanford is, I don't know if you've ever seen the image of the pickup truck that's smashed into the side of it.
Yeah.
That's something else that's happened. Yes, the concrete shield has done great work, great service to science.
Any other questions?
Yeah, there's a couple of questions in the chat if you want to check that.
Great.
Yeah, one question is, how do you differentiate between distant events with huge masses and closer events with lesser masses? How do the signals differ?
Oh my goodness, that is a fantastic question. That's such a great question that, let's see, if you will permit me, I will see if I can pull up a quick animation. Okay, so I'm going to try and share my screen again. All right, so wonderful question. So the short answer to this question is that the masses of the system are going to govern its time frequency evolution. So that's going to change essentially the way the wiggles wiggle. So if we can measure the way the wiggles are wiggling, or the phase, if you like, then we're going to get a measurement of the masses. And once we know the masses, then we can scale that to our data and get the distance. And this gives you some idea of how that works in practice. So we have some data in blue. We're changing the mass of our system. That's our model in orange. And then once we've matched it in phase, we can scale it directly in distance. And that's how we get this direct measurement estimate of the distance.
Great. And the other question was, when Betelgeuse was dimming back in December, January, there were reports of gravity waves detected nearby. Did anything come of that?
Right, yes. So that's true. So we do also, so I've talked a lot about searching for events from compact object mergers. We do also search for what we're not expecting. So we look for consistent patterns in the data between our network of detectors that aren't necessarily compact object mergers like neutron stars and black holes. So anything that we detected as significant, we would have released in an open public alert. There was also a, not at the same time if I'm remembering right, but there was also a gravitational wave burst event that was released at pretty low significance. I suppose I'll lead with the caveat there that if we did detect gravitational waves from a core collapse supernova, it would definitely have to be not only galactic, but less than half the distance between the Earth to the center of the Milky Way. So Betelgeuse is one of the likely candidates, but you would definitely have some visual confirmation if we were to see a gravitational wave signal. It would have had to be from the core collapse.
Hello, it's Brian.
Hello.
When you were discussing the multi-messenger approach to observation and so on, you mentioned that the time frame of the arrival here of the event in the various messenger modalities. And you mentioned that the gravitational waves of that event occurred first before the electromagnetic spectrum of detectors picked up on the same event. So that made me well, that was interesting to me because I thought that nothing goes faster than light and its buddies on the electromagnetic spectrum. But you were mentioning that there was a sequence. There was a sequence, like they didn't all arrive at the same time.
That's true. But
So is there a common man's explanation for that?
Yes, I think I can help there. So we do expect that gravitational waves and light travel at exactly the same speed. That's the speed limit of the universe, and they both, all waves of that nature where you have some kind of a massless particle, whether it's a graviton or a photon or another particle, they'll all travel at the speed of light. So we expected to see that delay. So you get a gravitational wave signal, it's sort of consistent, it's rising in amplitude, and then you get the peak amplitude from just as the two stars are merging. And then it is expected that you get about a second or two of delay before the material that's accreting will be released in the relativistic jet. So that's a physical delay that you would also have observed if you were standing right there.
Jessica, the question from Steve Bedingfield, who says, backing up a bit, so gravitational waves deform 3 space. How do they deform time, and how would you know?
Ah, fantastic. So the way that I like to think about this is that we are best able to measure in terms of translating the deformation of space-time, we're best able to translate that into this relative change in distance in space. But that being said, so of course space and time are correlated in this way. So instead of the analogy of the detectors as a ruler, so this is sort of the first place that I usually go to, the relative stretching and squeezing, thinking of them as a ruler, that's not quite right. They're actually functioning more like a timer. You're timing essentially how long it's taking a photon to get down to one of those mirrors and back relative to its partner. That's actually what the difference that we're measuring there is, the difference in phase, the difference between the time that it takes for the photon to travel, that relative change in distance. So they're completely related in the sense that if we understand the relative stretching and squeezing of the distance, then we also know necessarily how much extra time it's going to take that photon to travel.
All right, thank you very much. I think we should probably let you go. We had some excellent questions. You're going to be back for the GA Light on the 20th, Saturday the 20th, I believe.
This will start to look familiar.
If you think of other questions, I would encourage you to jump into that session and check that out. I wish we could have had you here in person on the Sunshine Coast, but thank you so much for taking the time to join us on Zoom, and to everybody else all the way across Canada that jumped in with us as well.
Yeah, thank you, Jess.
Thanks, everybody. Stay well.
Yeah. Thanks for coming.
Are you
Jess,
Delighted immensely,
best of our
Jess.
visitors, guests. Thank you.
I recorded this to my computer, so if you know anybody in your center that missed it, let me know. We'll be able to get it to them.
Yes, I'm wondering, are you there?
I'm here.